In this video, we'll discuss a little bit more about how we can use the simple linear regression model. Specifically, we're going to talk about how we can use it for prediction. We'll also talk about some concepts such as the scope of the model, and then revisit the idea of derivative and how we got the model estimates for a simple linear regression. So first of all, regarding model prediction, our goal with model prediction is simply to use our line of best fit to come up with a best guess for a new point. So let's say that we have a variety of data points that we have a line to fit. And let's say that we would like to fit a new data point that doesn't exist yet at this particular x value. So we'll look at this x value here. Notice that the best prediction that we're going to get is on that best prediction line. So what we need to do is talk about how we can use the equation of that line to get the prediction. Because this is a line based on sample data, I'm going to be using y hat. That's my best prediction line. Remember, if this were based on population data, I would use the expected value of y. And let's say, for the sake of argument, that my intercept term is 1. This is going to be b0. And my slope term is 2. This is going to be b1. And recall that there's no error term at the end because this is a best guess. If I want to predict what the y value will be at a given x value, all I have to do is plug the x value into my equation to get what the y value is going to be. Thus, if I want to understand what the y value, or calculate what the y value will be, if x is, say, 3, I simply plug in 3 into this equation for x. So 1 plus 2 times 3. In this case, my y value, 2 times 3 is 6, plus 1, my y value would be 7, and this would be my predicted value. And it really is that simple. Simply plug in your x value, and you can get your predicted y value. Plug in your independent variable, and you can get your outcome. Now, this is a really handy deal, but there are some limitations to what we can do, and it has to do, one of the limitations anyway, has to do with what we call model scope. So let's say that I have a whole bunch of data points, and I create a really great line around them here. And let's say, for the sake of argument, that someone wants me to predict an x value that's way out here. Well, I could extend my line to try to get to the point that they want me to predict, and I could use my equation. I could plug in my x value to whatever my equation is. I would use b's for the if I were fitting sample data. So I could plug in my x value, and then I would get a predicted y value, right? The equations don't break here. I can use them. The problem is that all of my data is right here. This is where all of my data lies. So when I go all the way out to where this x value is, this is super far away from any actual data that I've observed. This is called model extrapolation. Extrapolation just meaning I'm taking the data I've observed and I'm assuming that the pattern continues. Now, this assumption sometimes works out, but sometimes the true pattern of the line isn't particularly linear as we go far out. In fact, if it's not particularly linear, extrapolation may give us a really bad estimate. That is, our error may be greatly increased. And again, the reason that we may know that this could be a bad estimate is because we don't actually have any data points in that area. The data from our sample are all from a much smaller area in a lower range of x in this particular visual example. Thus, when we're talking about the extrapolation issue, we want to make sure that when we're predicting values, it sticks close to our range of x. Now this does not mean that you can't look at a value that's a little bit bigger than your x and try to get a prediction even if it's a little bit outside of the range of your x values. What it does mean is that you don't want to go way outside of the range of the x values. Another way this is sometimes phrased is that the scope of the model. The scope of the model that we've created is within this small range of x values. It does not extend out indefinitely. So our model scope is actually much more narrow than what we would want to be able to predict this point. And again, this isn't good or bad. This is just saying that this is where our data are. So if I were asked to predict something with an x value way out here, what I would likely do is mention that I don't have any data to support such a prediction and advise that maybe we can get some data to make sure that our model does continue out linearly, or to see maybe our model peaks off or our model starts to increase in some odd ways, or maybe just different things happen out in these x values than they do in the x values from my sample. So the final thing that we're going to talk about in this chapter is to look at some of the details of the derivative. Now, we had talked about the least squares error, and we had discussed how this is the sum from I equals 1 to n of the error term. We had mentioned, or excuse me, the squared error term. We had mentioned that you simply take a derivative and set the derivative equal to 0 to find the beta 0 and beta 1 values that minimize the error. And again, we either use the epsilon, beta 0, and beta 1, or we use E, B0, and B1. So for this theoretical proof, I'm going to leave it in terms of epsilon, beta 0, and beta 1. But when we're working with real data, remember that this is going to be B0 and B1 that we're going to use. I figured that as a closing thought, because you're going to have a homework assignment that does something like this. Now let me speak to your homework assignment. In your homework, the proof is not what I'm about to do. In your homework, the proof is a different proof. It's on a different model. So here our model is y equals B0 plus B1x plus epsilon. I believe in your homework proof it's y equals beta x plus epsilon. So note that there is no intercept term in your homework proof, and that's going to change all of the values that you're going to look at. So you're going to be looking at different outcomes. So please don't just copy this proof for your homework. Now the first step I'm going to do when I'm going to solve this is I'm going to write it out. So the sum from I equals 1 to n of y sub I, this is my observed value, minus y hat sub I, this is my predicted value, squared. And I'm going to save myself some writing here and do some copying and pasting. So here I'm going to replace my predicted value with what we know the prediction to be. That is beta 0 plus beta 1 x sub I. And this quantity is going to be squared. Now eventually I'm going to take a derivative, and I could actually start by taking the derivative right now. What I'll do though first is I'm going to write some of this out. So I'm going to square this term out, sum of I equals 1 to n. So if I square this term out, then if it's going to be, remember, a squared minus 2a times b plus b squared. So a squared, this is going to be y sub I squared minus 2 times y sub I times b0 plus b1 x sub I plus b0 plus b1 x sub I quantity squared. Now I'm going to distribute this sum out into its different components. So remember, the sum of the differences, or the sum of the sums, is the sum of the sums, or the difference of the sums. So here we're going to sum I equal 1 to n y sub I squared minus 2. Remember, you can factor constants out of a sum. I equals 1 to n times y sub I. And I'm going to actually distribute this y sub I in this step too. So y sub I times beta 0 plus y sub I times beta 1 times x sub I. And remember, you can rearrange these terms around if you want to. I'll do that in a bit. Plus the sum from I equals 1 to n of beta 0 plus beta 1, not beta I, beta 1, x sub I, quantity squared. And remember, you can't distribute a sum into a squared. You can distribute a sum into something that's just added together, but you can't distribute it into a squared. So the last step that we'll do is distribute this sum into this middle piece. So the sum from I equals 1 to n y sub I squared minus 2. Now the sum of this, beta 0 is a constant, so I can factor that out. Beta 0 times the sum of I equals 1 to n of y sub I, plus beta 1 is also a constant, so I can factor that out. Now remember, this negative 2 needs to be factored into all this as well, so this is going to be plus a negative 2 times the sum from I equals 1 to little n. Excuse me, I was going to also pull out that beta 1 of y sub I times x sub I plus the sum from I equals 1 to n of beta 0 plus beta 1 x sub I quantity squared. Woo! I could fit it all in. Okay, so this is going to be my starting point that I'm going to use to jump off and get my derivatives. This is going to be where we're going to start from. So I'm going to take the derivative with respect to beta 0 to get the solution for beta 0, and the derivative with respect to beta 1 to get the solution for beta 1. I'm going to start with the beta 0 one, and then we'll move on to the beta 1. So if I take the derivative of this entire thing with respect to beta 0, well, the first term becomes 0. There's no beta 0s involved. The second term becomes minus 2 sum from I equals 1 to n of y sub I. So the beta 0 carry down the power, and then beta 0 it goes to the 0 power, so it just becomes 1. This next term doesn't have any beta 0s in it, so that just becomes 0. And the final term, well, now we have to use a bit of our rules of derivatives. I equals 1 to n. It's the derivative of the outside, which is 2, times beta 0 plus beta 1 xi. So that's the derivative of the outside, and then times the derivative of the inside. Well, the derivative of the inside is just 1. So we're not going to have anything special there. And we're going to set this derivative equal to 0. So I get 0 equals negative 2, sum from I equals 1 to n of y sub I, plus, and now I can go on and start factoring out some different pieces and distribute this sum in, because now it's no longer squared. So it's going to be plus 2 times the sum of I equals 1 to n of beta 0, and I'm not taking beta 0 out, we'll talk about that in a sec, plus 2 times the sum from I equals 1 to n of beta 1 x sub I. Now all these 2's can cancel out, so we just divide everything by 2. Then we can go on and add this to the other side. This is the only negative one, so we end up with the sum of I equals 1 to n of y sub I equals. Now, what's interesting is, remember our rules of sums. Beta 0 is a constant over I, so it's not going to do anything. It's just like a c. But when we add a constant over I, what we end up with is n times that constant, or the limit of the sum. In this case, that's n times that constant. So this is going to be n times beta 0. plus, then we have beta 1 times the sum of I equals 1 to n of x sub I. Now, we want to get beta 0 all by itself, so we're going to need to divide everything by this n value. Now consider that when we have the sum of y divided by n, we had a term for this. This was y bar. When we have the sum of x divided by n, we have a term for this. This is x bar. Subtracting beta 1 times x bar from both sides, we get y bar minus beta 1 times x bar as our solution for beta 0. And this is our derivation. The other derivation's slightly more complicated. I'm going to copy this if I can to get us started, and we may or may not make it through the whole thing in this video. We'll see what we can do. The derivation in your homework for this second one is much easier, so don't worry too much about it. Now we're going to take the derivative with respect to beta 1. So again, we're going to set this derivative equal to 0. This first term has no beta 1s in it. This second term has no beta 1s in it. This third term, negative 2. This has beta 1, so this is going to be negative 2 times the sum I equal 1 to n of y sub I x sub I. And this last term also has beta 1s in it, so this is going to be plus the sum of I equal 1 to n. Now we take the derivative of the outside, so that's just the same as it was before, beta 0 plus beta 1 x sub I. But now we take the derivative of the inside, and the derivative of the inside is beta 1 times x sub I. So if we take the term on the inside that we care about is beta 1 times x sub I. So if we take the derivative of that, that's going to lead us with another x sub I. Reducing a lot of this noise, we get 0 equals negative 2 times the sum from I equals 1 to n of y sub I x sub I plus 2 beta 0 times the sum from I equals 1 to n of x sub I plus 2 beta 1 sum of I equals 1 to n of x sub I squared. Now, just like before, we can cancel out these 2's. We can move this to the other side, so we get the sum of y sub I x sub I equals beta 0 times the sum from I equals 1 to n of x sub I plus beta 1 sum from I equals 1 to n of x sub I squared. Now, it seems like we're almost stuck, but what we can do is we can sub back in the term for beta 0. So remember, we already solved for beta 0, but we can take those terms and solve for them again, or undo what we already did. So up here we had beta 0 is y bar minus beta 1 x bar. Now y bar was just the sum of y divided by n, and because we're doing multiple sums here, I want to be careful, so we'll just use j for these ones, j from 1 to n of y sub j minus beta 1 times sum from j equals 1 to n of x sub j over n. I'm using j because we already have I as a sum, and we don't want to get these two sums confused. This one is a different sum than that one is. Though they're still going from the same base, as we add them together, we just want to make sure that we keep them distinct. Now all of this is going to be times the sum from I equals 1 to n of x sub I plus beta 1 times the sum from I equals 1 to n of x sub I squared. Now we're going to distribute our sum in, so we're going to get the sum from I equals 1 to n of y sub I x sub I equals the sum from we're using j equals 1 to n y sub j times the sum of I equals 1 to n of x sub I divided by n minus beta 1 times the sum of j equals 1 to n of x sub j times the sum I equals 1 to n of x sub I divided by n plus beta 1 times the sum of I equals 1 to n of x sub I quantity squared. Now, this term up here, that we have different numerators, note that these letters are just meant to be distinct, but these concepts are the same. This is adding up from all the x's from 1 to n. This is adding up all the x's from 1 to n. So actually these two can be combined here, which is nice. The y's and x's can't be combined, but if we do combine those values, what we're left with is the sum equals 1 to n of y sub I times the sum I equals 1 to n x sub I, and I know I've changed my numerator in y, or my iterator in y. That's going to be okay. Minus beta 1 times the sum of I equals 1 to n of x sub I quantity squared. And again, I always start by keeping them separate, but as long as the concepts are maintained, like here, the concepts don't get mixed up, then we're okay to write them in the same notation. Beta 1 times the sum of I equals 1 to n of x sub I squared. So what we need to do here is get our beta 1 out from all of this yucky mess, and this is a yucky mess, and then start to get beta 1 by itself. So I'm actually going to start by subtracting this over to the other side, this first term. So we're going to get the sum from I equals 1 to n y sub I x sub I minus the sum of I equals 1 to n of y sub I times the sum of I equals 1 to n of x sub I, and these are distinct sums. So instead of using different letters, I'll just write them in parentheses there, divided by n, equals, now I'm going to pull out the beta term over on this side. So we'll have beta 1. And then, so that we have the minus side on the second side, or the minus sign on the second side, I'll actually switch the order of these. So it'll be the sum of x squared divided by, or excuse me, minus the sum of x quantity squared divided by n. Last but not least, to get beta by itself, we divide both sides. So what we end up with is I equals 1 to n y sub I x sub I minus sum I equals 1 to n y sub I sum I equals 1 to n of x sub I divided by n. That's all in the numerator. Now this divided by the sum of I equals 1 to n x sub I squared minus the sum of I equals 1 to n of x sub I quantity squared divided by n. And you'll notice the similarities in the top and bottom here. That's because this top is the sum of squares of x, y, and this bottom is the sums of squares of x. So this is our proof. There's one more step that you can take it to find the other version that we had. Recall we had I equals 1 to n of x minus x bar times y minus y bar, y bar, divided by sum of I equals 1 to n of x minus x bar quantity squared. You can get to there from here. I'll leave that proof to you if you're interested. But these are our derivations and how we would go about using the derivatives to find our estimates and the equations that we would use to find B1 and B0. Again, I'm using betas here because I'm using the theoretical epsilons. If we were using the residual terms, all of these betas would be B, but the process would still remain the same. This video has been a brief description about how we can predict using regression. It's talked a bit about the scope of the model and then went a little bit more in depth on some of those derivatives, as you'll be asked to do simpler derivatives on a homework problem. And again, I promise that the idea is the same, but the derivatives you'll be doing in your homework are quite a bit simpler.